In this lesson, we're going to be starting into a new unit called Integer Properties. At the end of this unit, will be working with cryptography systems. Specifically, we're going to be learning about the RSA cryptography system, which is a very secure encryption system. But before we can understand this and be able to encode and decode a message, we're going to need to learn some new terminology and some new processes. We'll start by learning about the division algorithm. But before we really get into that, we need to start with some definitions. So let's talk about the word divides. What does that mean? So if we have two integers, x and y, then we would say that x divides y, denoted x and then the up and down symbol, pipe symbol, y. X divides y if and only if x is not equal to 0. Now that's just because we can't divide by 0, okay? So if and only if x is not equal to 0 and there is an integer k such that y is equal to k times x. Let's look at some examples so that you can understand what this is saying. So we would say that 3 divides 6 because there's an integer 2 such that 6 is equal to 2 times 3. So if you can find an integer k such that when we multiply that by the x, we end up with the y, then that's when we can say that x divides y. So 3 divides 6 because 6 is equal to 2 times 3. 2 divides 12 because 12 is equal to 6 times 2. We found a k6 such that when we multiply it by 2, we end up with the 12. Now, next we're going to talk about some definitions that I think you're all really familiar with. So if x divides y, then y is said to be a multiple of x, and x is a factor or divisor of y. So going back to our first example, 3 divides 6 because 6 equals 2 times 3, then we would say that 6 is a multiple of 3 and 3 is a factor of 6. Here, 2 divides 12 because 12 equals 6 times 2, so we would say that 12 is a multiple of 2 and 2 is a factor of 12. We denote the fact that x does not divide y by just putting a line through that pipe symbol, and that would say that x does not divide y. Now let's talk about what a linear combination is. A linear combination of two numbers is the sum of multiples of those numbers. So, for instance, if we're talking about 5 and 8 and we want to find some linear combinations of 5 and 8, we could say that 3 times 5 plus 7 times 8 is a linear combination because we're just taking a multiple of the 5, and 3 times 5 would be a multiple of the 5. And then we're taking a multiple of the 8, 7 times 8, and that's a linear combination. Now, the 3 and the 7, those are just random numbers I picked out. That could be any integers we put in there. That would also be considered a linear combination. So here's another linear combination of 5 and 8. And here, if we say that s and t are integers, then s times 5 plus t times 8 would be considered a linear combination of 5 and 8. This 3x plus 9y, we could say is a linear combination of an x and a y. Whatever the x and y values are, we're taking a multiple of each and adding them together, so that's a linear combination. Now, here's a theorem about the divisibility in linear combinations. It says, let's say that there are 3 integers, x, y, and z. If x divides y and x divides z, then x also divides sy plus tz for any integers s and t. So what did we do there? We took our the y and the z that that x divides both of those, and we took a linear combination of that. S, which is some integer, could be anything, times y, plus t is an integer, could be anything, times z. Adding those together, that would become a linear combination. So if x divides one integer and x divides another integer, then x would divide a linear combination of those two integers. Okay, so if x divides y and x divides z, then x divides any linear combination of y and z. So here's an example. We know that 2 divides 12 and 2 divides 24. So we would know for sure, as long as s and t are integers, as long as we can be assured that s and t are integers, we would know that 2 divides s times 12 plus t times 24 for any integers s and t. So because that is a linear combination of the 12 and the 24. Since 7 divides 14 and 7 also divides 21, we know that 7 divides, and then I've thrown in just some integers here, a 3 and a 5 for the s and the t. So we know that 7 divides 3 times 14 plus 5 times 21, again, because of this theorem above. So let's look at the proof for this. So we want to prove that, as long as x divides y and it also divides z, it also divides a linear combination. So first of all, we know that x divides y, so that implies that y is equal to k times x for some k, right? Some integer k. And we also are assuming that x divides z, and that implies that z can be written as a multiple of x. So we'll use j as that multiple of x. So both of those assumptions assume that y equals kx and z equals jx. So let's take the sy plus tz, that's the linear combination. That's what we're trying to prove x divides. So we got that, but let's replace the y with the kx and replace the z with the jx. And so when we put that together and we can factor out the x, you see now we have that linear combination equals sk plus tj times x. Now, sk plus tj, since s and t are integers, and k and j were integers, we know that sk plus tj is an integer. Now that's not from this theorem, that's just something that we would know to be true. Then we've written that linear combination as this multiple of x, right? The sk plus tj, we would say would represent some integer multiple, and then that times x then would be the multiple of x. So since we can say that's true, then we have shown that x divides sy plus tz. Okay, so let me go over that proof one more time, just in case you missed it. So remember that we've got this first line of the proof. Those are some assumptions that imply these different things, the red equation and the blue equation. So then we start with this linear combination, and we're trying to see if we can write that as a multiple of x. If we can, then that means that x divides this. Okay, so what we do is then just replace the y and the z with what we saw that it was up above, and then we factor out the x, and we see that yes, that linear combination can be written as a multiple of x. And so as long as something can be written as a multiple of x, where that multiple is an integer, then we know that we could say that x divides that thing. So we've shown that x divides a linear combination. Next, we're going to talk about the modulus operator, and most of you, I think, are familiar with this, but we're going to go over it and then also talk about the div operator and hopefully then feel really good about distinguishing the differences between the mod operator and the div operator. So let's start with the mod operator. What would we say that 12 mod 5 is? Well, what we do, this is the way I like to think about it, we would take as many 5s as we could and throw them out of the 12 until we can't throw out any more before we would go below 0. So I start with 12, throw out a 5, throw out another 5. I could throw out 10 and still be above 0, and I would end up at 2. Okay, so we start at 12, throw out as many 5s as we can. 12 mod 5 is where we end up without going below 0. So we would end up at a 2. It's the remainder after we throw out some 5s. Okay, 10 mod 3, we'll start with 10, throw out as many 3s as we can, and then 10 mod 3 is where we end up without going below 0. So we throw out 3 3s, and we would have thrown out 9 by that point, and then there's only 1 left over. So 1 would be the remainder, and so we'd say that's the value. 14 mod 7, we throw out as many 7s as we can, and that we can throw out all the way down. We can get down to 0. Since 14 is a multiple of 7, then we can throw out 2 of those, and then we end up at 0. So in this case, we would have a remainder of 0. That's where we would end up after we throw out as many 7s as possible. And here, 141 mod 100. We start with 141, throw out as many 100s as we can, and stop before we go below 0. And so where would we end up? We would end up at 41. Now the div operator, that's similar to the mod operator, because if we're looking at 12 div 5, we're still going to start with 12 and throw out as many 5s as possible. But the 12 div 5 would be how many times we can throw out a 5. So if we start with the 12, we can throw 5 out once, 5 out again. So we can do it 2 times. Now this example here turns out that 2 was the answer we got when we took 12 mod 5 also, because 2 was the remainder. But in this example, we can also throw out 2 5s, so 2 would be the answer for this also. So it's a different 2. In this case here, that's how many times we can throw out a 5 before we get below 0. Here, 10 div 3, how many times can we throw out a 3 before going below 0? We could throw out 3 3s. So we would say the answer is 3. The next one, what is 14 div 7? Well, how many times can we throw out a 7? That would be 2 times. And what's 141 div 100? How many times can we throw out 100? And that would just be 1 of them. Okay, so remember that the modulus operator, the one that we talked about in the last slide, that is what the remainder would be after we throw out these, multiples of a certain number. But the div is how many times we got to throw them out. So this is kind of a picture of what you'll see in, I think, a participation exercise in Zybooks. And so we're looking at 15 mod 6 and 15 div 6. In both cases, we're starting at the 15. But for 15 mod 6, we'll throw out as many 6s as possible and then figure out where we end up. And we end up at the 3. But for 15 div 6, we'll throw out as many 6s as we can, and then we find out how many of those we can throw out, and that answer would be a 2. Take a look at this example here when we are taking 74 and dividing by 3. We're using long division, and when we go through that, I think you probably remember how to do long division. We would end up getting all the way through. We could say that we've got a 2 first, and then we end up being able to put a 4 up there above the the top line, and then we would end up with this 2 here and no more digits to bring down in the right column, and so we'd be stuck with the 2. And so one of the things that we learned that we could do in that case is just stop there and say there's a remainder of 2. And there were other ways to go about it. We could go further, but in this case here, let's just talk about stopping with that remainder. So if we stop with that remainder there, we would say that 74 divided by 3 is equal to 24 with the remainder of 2, right? So think about this. If we took 74 mod 3, these are the same numbers, we end up with a 2. So the modulus operation results in that remainder that we would have got if we had gone through this long division. But the 74 div 3 would end up being that quotient that you would get before the remainder. So the div operation produces the quotient. The mod operator produces the remainder. Here's another example. 46 divided by 2. In this case, if we did long division, we'd find that we don't have a remainder. And again, if we compare what we have over there on the left to these modulus and div operators, we'll see that how they correspond to what we have over there in the long division. 46 mod 2 would end up being 0, and that's the remainder we got with that long division. And 46 div 2 would be, what that quotient would end up being, and so that would be 23. So, there's nothing new here. It's just another way to look at that modulus and div, that if we were doing long division, the mod would represent the remainder, the div represents the quotient. Now, what would we do if we're trying to find the div and mod of a negative number? You might not have heard of this, and it's different than what you would think. You would think that you would just maybe get the answer assuming that that negative wasn't there, and then your answer, you would just throw a negative on there. But that's not what we do here. So here's a picture of what we would do if we're trying to find negative 11 mod 4. So look at the number line down there. We started the number negative 11. Now in this case, we're not going to be throwing out 4s, but we're going to be adding in 4s. And we're going to add in as many 4s as we can to get to a positive number. So we need to get past the 0 into the positive zone. So if we start at negative 11, add in 3 4s, you see that we'd finally get above the 0, and where would we end up? At the 1. So wherever we end up, once we get past the 0 into the positive zone, that's what our mod value would be. So negative 11 mod 4 would equal 1. Now the div would be how many times do we get to add in that 4 until we get to the right spot. So we added 4 3 times. But here's where we have to throw in that negative number. We add 4 as many times until we get into the positive range, but because we added instead of threw away 4s, then we need to change that sign. So we would put a negative 3 there to show that we had to add in the 4s instead of take away the 4s. So negative 11 div 4 would be negative 3. So we've already been talking about long division and seeing some examples of this. Let's look at this example here too again. 74 divided by 3. If we went through this process and got a 24 up above, ended up with the remainder of 2, then we could say that our answer is 24 remainder 2. But what we could also say, if we wanted to decipher what this means, is we could say that 3 times 24 plus 2 would end up giving us the 74. 3 times 24 whatever we have on the outside of that, in that green box, the 3 on the left, the 24 above, those two things multiplied together, adding the remainder, will give us what's inside that box. So if I were to ask you to divide 74 by 3 and tell you to use integer division, what that would mean is just do what we did there. Stop with the remainder and then just tell me what you would get. So this integer division is different than what we normally think of as division. So we would just say that 74 divided by 3 is equal to, and then we would say 24 remainder of 2. If we had 9 divided by 4, we could say 2, 4 would go into 9 2 times, but then we'd have a remainder of 1. And that's how we would answer our question of what is 9 divided by 4 if we were doing what's called integer division. Now we have a theorem that tells us that we get a unique answer anytime we perform an integer division problem. So if you give me two numbers and say, do some integer division, I will get an answer, and then if you do it, you would get an answer. All this theorem is saying is that we would always get the same answer. It's not like I would get one thing and you'd get another. So it seems kind of obvious, but it's important because we do use this information at some point later on. So this theorem is called the division algorithm, which is a little weird because it's not an algorithm, it is a theorem. Anyway, here's what it says. I'll read it first, then we'll look at an example because it might not make a lot of sense at first. Okay, it says let n be an integer and let d be a positive integer. Then there are unique integers q and r, with r being between 0 and d minus 1, such that n equals q times d plus r. Now remember, we're starting with the n and the d. And it's saying that, we have, we're actually, doing a division, taking n, dividing it by d. And this is saying what we could end up writing it as. If we do long division, it would be whatever the quotient is, times that divisor, plus the remainder. And this is just saying that these are the q and the r that we would come up with would be unique. We couldn't get more than one set of answers here for any given d and n and d. Okay, so the q stands for the quotient and r stands for the remainder. So let's look at this example and see that this really isn't saying anything more than what we've already talked about. So if you look over on the right in the little green box, you see that we took 74 divided by 3 and we got a 24 with the remainder of 2. So all this is saying is, if we start with n equals 74 and d equals 3, then we would come up with some numbers such that we would be able to write n, which is our 74, as the divisor times this q, and so we saw that's the quotient. That would be the 24. So basically it's just saying we can write 74 as the quotient times what we were dividing by, so 24 times 3 plus 2. Okay, so just basically what you would be able to say if you did this integer division here. Now, something that's interesting here is that the what's considered q in this n equals qd plus r is, again, that quotient that ends up being these two numbers, 74 and 3, using the div operator, 74 div 3. And we already said that in a previous slide, that the div result ends up being the quotient, right? So that's the q for the quotient. So 24 is 74 div 3, and then that remainder would be the 74 mod 3. Okay, so we can rewrite 74 as 74 div 3 times this divisor of 3 plus 74 mod 3. That's all this theorem is saying, and it's saying if you do the problem, you'll get the same answer. Now we're going to talk about some arithmetic that's kind of some strange arithmetic. It's called modular arithmetic. If I asked you, can I ever add 2 and 4 and get 1? You would say probably no. 2 plus 4 is always 6, never 1. But if I use modular arithmetic, I could get a 1. So this kind of arithmetic, if I'm talking about a certain addition, I could say addition with a certain mod to it. So addition mod 5. So if I'm doing this addition, not just regular addition, but addition mod 5, I could get 1. So what that involves is, if you're taking two numbers, then adding them together and applying this mod to the result, that is addition mod m. So if I'm doing 2 plus 4 with addition mod 5, I would take the 2 plus the 4, which gives me a 6, but then that result of 6, I take mod 5 of that, and so I end up with 1. So 2 plus 4 using addition mod 5 gives me a 1. Can we ever multiply 3 times 6 and get a 2? Well, if we're doing multiplication mod 4, we can. So just like we did with addition, we can do this with multiplication. So I could say I'm going to take the 3 and the 6, multiply them together, and then take mod 4 of the result. That would be like applying, that would be multiplication mod 4. So 3 times 6 is an 18. But if I take mod 4 of 18, I do end up with 2. Now, you're not going to have to be, I'm not going to ask you these questions like, could we ever multiply some number times another and get this other number? You don't have to come up with that. These are just examples of how we would get strange answers if we do this special kind of arithmetic. So you do need to know how to do this special kind of arithmetic, but you don't have to come up with what I showed you here. Once I ask you a question, you wouldn't have to come up with what is it? Is it, mod what is it? You're not going to have to come up with that. I just want you to understand how modular arithmetic works. Okay, what is a ring? So sometimes in mathematics we have some interesting definitions, and this is one of those. A ring in mathematics is just this. It's a set of integers starting with 0 up to some certain number. We'll call that m minus 1. So this set of integers, 0 up to m minus 1, along with some operators, addition mod m and multiplication mod m, that defines this closed mathematical system, because if I take any of those numbers in the set and apply addition mod m or multiplication mod m, I end up getting a number still inside that set. I don't get any new number outside that set. So it would be considered a closed mathematical system, and we call it a ring, and we'll denote it like this, z sub m. So z, remember, is represents the integers, and if we have a subscript of m, that just means we only have m integers in there, and it's going from 0 up to m minus 1. So it's really pretty simple. So z sub 9 would be involving the set 0 up through 8, and then having the operators addition mod 9 and multiplication mod 9. And that would represent a closed mathematical system, because if we take any of those numbers and apply these operators, we would get one of those numbers back. So in this case here, what would we say the value of 3 times 4 is in z sub 9? If we say in z sub 9, that means we can only use those operators, addition mod 9 or multiplication mod 9. So if I want to take 3 times 5, that means I'm really wanting, 3 times 4, that means I'm really wanting to take 3 times 4 and then applying mod 9 to it. So 3 times 4 is a 12. If we take 12 mod 9, we get a 3. So we would say the answer is 3 to this question. What's the value of 5 plus 4 in Z6? So in Z6, we would just be dealing with numbers 0 up through 5. And if we say 5 plus 4, that means we're going to add 5 plus 4, but then we need to take mod 6. So we really want to do 5 plus 4, which would be a 9, and then take mod 6, and we end up with a 3. So the answer to that question is a 3. Okay, here's another definition, congruence mod m. So let m be an integer greater than 1, and let x and y be any two integers. Then we would say that x is congruent to y mod m, and that's kind of all together. It's not like x is congruent to y mod m. It's x is congruent to y mod m if x mod m equals y mod m. So, and we'll look at some examples here. So if it's true that x is congruent to y mod m, then we could denote it this way with 3 equal signs and then say what the mod is, because, you know, they could be congruent in one mod, but then not congruent in another mod. So could we say that 11 is congruent to 5 mod 3? Yes, we could, because if we take the mod of both of those, do we get the same thing? 11 mod 3, 5 mod 3. Well, let's see. 11 mod 3 would be 11 mod 3 would be 2. 5 mod 3 would be 2. I didn't have those answers there. Okay, now on to the next one. 24 is congruent to 19 mod 5 because 24 mod 5, so what would that be? That would equal 4, right? Because I'm throwing out 5s and I end up with a remainder of 4. And then 19 mod 5 is also 4. So if those two, are equal, then we would say that 24 is congruent to 19 mod 5. Again, we just take mod 5 of both of those and see if they're equal. Now here is another way to determine if two numbers are congruent mod something. Let's let m be an integer greater than 1 and x and y be any two integers. Then x is congruent to y mod m if and only if m divides the difference. Okay, so this is then can give us an easy way to tell whether two numbers are congruent in a certain mod. We just take the difference of the two numbers and see if m divides that. Okay, let's look at an example. We just saw that 11 is congruent to 5 mod 3. So this alternate characterization says that if that's the case, then 3 would divide the difference. So 11 minus 5 is a 6, and 3 does divide 6. So we see that it works. It's true. Here's another. We saw that 24 is congruent to 19 mod 5. Does 5 divide that difference? 24 minus 19 is 5, and yes, 5 divides 5. So we see that's true. And so sometimes that's an easy way to tell if two numbers are congruent in a certain mod, is just take the difference of the two numbers and see if m divides that. So this is a picture of an activity that you'll need to do in zyBooks. And I'm not showing you what it looked like at the beginning, but I'm showing you what it looks like after you finish it up. So I want to just kind of show you so that you get an idea of what you're supposed to do in this activity. So here it says match two numbers if they're congruent mod 11. Now see these numbers over here, 88, 5, negative 8, 39. Those numbers start, well, let's see. It's either those numbers that start at the top Or maybe the 0, 60, 24, 25, 17 start at the top. But one of those sets of numbers start at the top. And then you drag them over so that you get two numbers on the same line that are congruent. In this case, they're congruent mod 11. So again, I either drag the 88 over or I drag the 0 over, and I can, put them in any order. But what we want to do is put the two together that are congruent mod 11. Now, one way to do it is that original definition as find find the number mod 11 and find another number mod 11 and see if they're the same number. But in this activity, this alternate way ends up being easier. Okay, so remember, the alternate way is to take the difference of the two numbers. If they're divisible by whatever you're taking the mod of, then we say they're congruent with that mod. So notice 0 and 88. The difference between those two is 88, and we know that 88 is a multiple of 11. So those would be congruent mod 11. So whatever I started with, blanks either on the left or blanks on the right, I would drag the number over to match the 0 and the 88 to have them on the same line, because we know they're congruent mod 11. Now, if I compare 60 and 5, I just, find the difference. That'd be 55. Again, we know that's that's a multiple of 11. So we know those would go together on the same line. 25 and negative 8 goes on the same line, because if we subtract 8 from 25, let's see. So yeah, 25 minus, remember it's a difference. So we're going to take 25 minus a negative 8. Or we might, in this case, it shows the other way around, negative 8 minus 25. But because we're subtracting a negative kind of thing, we have to be careful here. It's not going to be a, 17, right? It's going to be, we could look at the negative 8 minus 25. That gives us a negative 33. But if we did the difference the other way around, 25 minus a negative 8, we would get a positive 33. But in either case, we would end up with something that 11 evenly divides. So that's why we would see that these should go on the same line together. And then 17 and 39, the difference there would be 22. And again, that's something that's evenly divisible by 11. So anyway, in that exercise that you see in Zybooks, you're just going to want to make sure that the numbers are on the same line that are congruent mod 11. So you just want to find the difference between them and see if that's if 11 evenly divides it. Now, this is an interesting little theorem that is kind of a side note. We're not going to spend a lot of time doing problems like this, but it's talking about computing arithmetic operations mod m. It's saying that if we have m being an integer larger than 1, and then x and y are integers, then if we want to take x mod m and add y mod m, and take mod m of those, it's the same as if we were to take just the x and the y first, add those together, and take mod m once. So it's saying we can either, apply mod m all over the place there, or as on the right, just add them together and apply mod m once. And it's true also for multiplication. So either, if we're talking about x times y, and then we want the mod m, we could say take x mod m, y mod m, multiply those together, and then take mod m of that. So we can do it either way. We can either do the mod m once at the end or do it a bunch of times. Now you might think, well, why would I want to do it a bunch of times instead of just doing it at the end? Well, here's an example, and I think you might have a problem in Zybooks to do like this. We can use this theorem to find this calculation pretty easily. So I've got 41 to the 38th plus 37 times 90 mod 8. Now, normally what we would have to do if we didn't have this theorem and know that this is to be true, this is true, then we would need to find out what 41 to the 38th is. That would be, we've got to get a calculator out and, we'd get a pretty big number. And then we'd have to take 37 times 90 and find out that. But using this theorem, we could just apply the mod 8 inside all of those calculations there. I mean, all of those expressions there. So we could put the mod 8 in with the 41 and the mod 8 next to the 37 and the mod 8 by the 90. So here's where this simplifies things, because 41 mod 8 is a 1, right? Because I can throw out a bunch of 8s and that would represent 40, and I just have 1 left over. So the 41 mod 8 is just a 1. And 1 to the 38th, in this particular example, this helped a lot because we know that we can find 1 to the 38th very easily. It's just a 1 because 1 times itself as many times as we want always turns out to be 1. And then the 37 mod 8, that would give us a 5. The 90 mod 8 would give us a 2. So now we have a much simpler calculation. So we would have the 1 plus a 10, right, would give us an 11. And then we need to apply mod 8 just again. And so then we would end up with a 3. So again, this theorem just says we can either just do it once at the end or just all over the place. Now notice we didn't do it in the exponent because this doesn't say we pull in the mod from the exponent. I didn't find mod 38 mod 8. It's just into all the, additions and multiplications. Now we're going to talk about prime factorizations. Now, first of all, let's talk about what it means for a number to be prime. And I'm sure you've heard this before, so you're probably very familiar with this. A number p is prime if it is an integer greater than 1 and its only factors are 1 and p, right? So, for instance, we would say that 23 is prime because it only has factors of a 1 and 23. We can't come up with any other factors of that. 24 is not prime because it has all these factors of not only 1 and itself, but also 2, 3, 4, 6, and 8. Those are also factors. So because it has factors other than 1 and itself, then we know it's not prime. So is 33 prime? Well, if I can come up with more than 1 and 33 as factors, then I would say it's not prime. And I know that 33 is the same thing as 3 times 11. So that means that 3 is a factor and 11 is a factor. Along with 1 and 33. So we would say that's not prime. Now, the fundamental theorem of arithmetic says this: every positive integer other than 1 can be expressed uniquely as a product of prime numbers where the prime factors are written in non-descending order. Okay, so let's look at this example here. To find the prime factors, what you can do is do this little tree. This is how I usually do it. Start with, if I'm wanting to find, write 120 as a product of prime numbers where these are prime factors of 120, then I can start with the 120 at the top and then draw some branches and think, how can what two numbers multiplied together gives me 120? Now, I put 2 times 60. You see the 2 and the 60 there? That was the first thing I thought of at that particular time. But in your mind, you might be thinking 3 times 40. And that's fine if you do 3 times 40. So your tree could look very different from mine, but we'll end up having the same result. So don't worry if you wonder, what if you don't do the tree just like this? You do end up with the same result. So you just come up with a tree like this, where, at the end of each branch, you try to factor it some more, by, writing it as the product of two numbers. But then you see that there are some branches where you can't go any further. So like the 2's here, we would have to stop. Then we have the 3 and the 5, we'd have to stop. Now, let's look at all of the ends of the branches where we had to stop. And we see we have these numbers here. Then what this means is that we can write 120 as the product of these numbers. So I could write 120 as all of these multiplied together. But notice as part of this theorem, it says prime factors written in non-decreasing order. So basically, we would want to start at the low end and then just either stay there or increase, until we're done. So we've got 3 2's, so we'd start with the 2's, 2 times 2 times 2, and then we have 1 3, and then we have 1 5. So this is how we would write 120 as a product of prime numbers where these prime numbers are written in non-descending order. And if you had done a different tree, where maybe you started with 3 times 40 or 4 times 30 or whatever, if you put those in non-decreasing order, like I did, you would have the same result there. And that's all the fundamental theorem of arithmetic is saying. Now, we have a special definition, a word that we use called multiplicity. And the number of times a factor shows up in the prime factorization is called multiplicity. So since 2 showed up 3 times, we would say 2 has a multiplicity of 3. The number 3 showed up once, so we'd say it has a multiplicity of 1. I don't have it here, but 5 shows up once, so we would say the multiplicity of 5 is also 1. And we've expressed 120 uniquely as a product of prime numbers. And another thing we can do is, instead of saying a 2 times a 2 times a 2, we could use exponents. And so if we do that, this is the same, we would say it's really still the same, those same prime numbers being multiplied together. But if we do it that way, then it's the exponent that gives us the multiplicity, because we have 2 to the 3, that says that 2 is there 3 times. So that we can just, if we have it written like that, in exponential notation like this, then we can look at the exponents to decide what the multiplicity is. Okay, let's find the prime factorization of 75. So we could start with 75. The first two factors that I think of for 75 is 3 times 25. So I'll have a branch for 3 and a branch for 25. Now 25 can be factored further, so I could write 25 as 5 times 5. So I have a 3 and a 5 and a 5. So I could write this as 3 times 5 times 5. And then I have then written 75 as a product of prime numbers, and this theorem says that that's unique. You couldn't come up with a different way where you've got also prime factors and also written in non-decreasing order. You would have to get the same thing as I get. And again, we could use exponents like that. And 3 times 5 squared. And in this case here, we would say that 3 has multiplicity 1, 5 has multiplicity 2. Greatest common divisor. You may have be familiar with this. You may be familiar with this by calling it the greatest common factor. So the greatest common divisor, which we call GCD, of non-zero integers x and y is the largest positive integer that is a factor of both x and y. And again, it's called also the greatest common factor. So let's look at an example. If I asked you what is the GCD of 9 and 12, we'd be looking for some number that's a factor of both of those, and that's the largest factor of both of those. So 3 is a factor of 9 and 12. And we could think, yeah, that's true, but is there a number bigger than 3 that's also a factor of 9 and 12? But there would not be. So we would say that 3 would be the GCD. Okay, and again, you might be familiar with it as GCF, greatest common factor. We are going to be talking a lot about the GCD. So you might, in the book, the way the book talks about it, they use those terms, GCD, instead of greatest common factor. So you might want to start orienting your mind in thinking about GCD as opposed to GCF. What's the GCD of 24 and 16? We got to come up with a factor that's, that is a factor of both of them. That's the largest of all, and then we can't find a factor bigger than. So 8 would be the GCD because it's a factor of both of those, and there's no other common factor that's bigger. What's the GCD of 12 and 18? 6 is a factor of both, and there's no other common factor that's bigger. So you kind of just have to think through all of the different factors on both of those and find the one that's the largest. We're going to find another way to do this, though, here using a theorem here in a minute. But, when you have just these small numbers like this, that's kind of, you just want to kind of think through all possibilities and then think, is there any factor that's bigger? And if not, then you found the answer. If we find that the GCD of two numbers is a 1, then we would say that the numbers are relatively prime. Okay, so any two numbers would have a GCD, but maybe the greatest common divisor is just a 1, because any number has a factor of 1. So if we've got two numbers and the largest factor they have in common is a 1, then that means they have, they don't have any other common factors, and so we would say that those are relatively prime. What's the GCD of 25 and 9? Well, we could think through. Really, there are no common factors there except for the 1. So we would say those numbers are relatively prime. Least common multiple. You've probably heard about this before too. So the least common multiple of non-zero integers x and y is the smallest positive integer that is an integer multiple of both x and y. So if I have a 15 and a 10 and I'm asked, what is the least common multiple? I'm looking for the smallest positive integer that's a multiple of both of those numbers. Okay, so multiple of 15, those are that would be 15, 30, 45, 60, those would be multiples. And multiples of 10 would be 10, 20, 30, 40. So we want to find the multiple that the smallest one that they both have in common. And 30 would be the smallest multiple of both 15 and 10. The least common multiple of 6 and 9. That would be 18 because it's the smallest multiple of both 6 and 9. Okay, so here is a theorem that helps us find those easily, especially when those numbers are bigger. It's easy enough when we've got those small numbers to just think through all the possibilities and come up with the answer. But if we've got bigger numbers, then it's a little bit harder. Now, this picture of this theorem might seem a little daunting because you see that we've got numbers with these exponents, and the exponents are in terms of a Greek symbol, but it's really turns out to be much easier than you think it's going to be when you look at this. Okay, so let's read this and see if we can figure out what it's saying. So this is saying let x and y be two positive integers, and you see right below we have x equals and y equals. So we're going to have these two integers, and we're going to think about their prime factorization. So let x and y be two positive integers with prime factorizations expressed using a common set of primes. So x could be written as some different numbers, all taken to some different powers, right? It would just depend on what those um, what the prime factorization is, right? Y could be also be written like something like this too. And then it says the p sub i's are all distinct prime numbers. The exponents alpha sub i's and beta sub i's are non-negative integers. So we're going to have these, possibly some exponents there in our prime factorizations. So we have these prime factorizations, and what this theorem says is that we can know if x divides y. So if we so we can say x divides y. We can know that as long as the alpha values are always smaller than the beta values for each of those prime factors. Okay, so I write out x in terms of those prime factors using the exponents, write out y, and then if the alphas are always smaller than the betas, then we would be able to say that x divides y. That's one thing. Another thing we would be able to see, and we're going to see examples here, so don't worry if this isn't making a whole lot of sense yet. But the GCD of those two numbers, x and y, can be found by taking all of those, those prime factors there and taking it to the minimum of either the alphas or the betas. So for P1, I see there's an alpha sub 1 and a beta sub 1, which is the smallest. And I take all those smallest, the minimums of those exponents for each of the p's and multiply them together. That gives me the GCD. If I do the same thing but take the maxes, I'm finding the least common multiple. So let's look at an example to see if we can make sense of this. So 24, how could I write that in terms of common, first of all, let's find the prime factorizations of 24 and prime factorizations of 50. So if I were just looking at 24, and I were to write that prime factorization, in non-decreasing order, I'd have a 2 to the third times a 3 to the 1. That gives me 24. So why do I have this 5 to the 0th there? Well, forget about that just for a minute, okay? So normally you would not have that 5 to the 0 there. So you would just have 2 to the third times 3 to the 1. Then do the same thing for 50. For 50, you would have 2 to the 1 times 5 squared, because that's what the prime factorization would be. The 3 to the 0th is there. Don't worry about that. We wouldn't have that there normally, okay? But when we want to use this theorem, we want all of these numbers that are taken to these different powers to match in both of these cases, for the 24 and the 50. Well, 5 is not a prime factor of 24, but I could write that as 5 to the 0th, right? 5 to the 0th is just a 1, so it doesn't hurt to just multiply all of that by a 1. And the reason I want to do that is because 5 shows up in the other one. So if there's a prime factor that shows up in the other number, we're going to put it in this number, but take it to the 0th power, and that doesn't change anything. So because 5 shows up in the 50 prime factorization, I'm going to put a 5 to the 0. And in 50, because 3 shows up in the 24 prime factorization, I'm going to put a 3 to the 0. So now you see that I have the same numbers, 2 and a 3 and a 5. And if you look up in that theorem, you see that at the very top, x equals p sub 1 up through p sub r, and then y equals p sub 1 up through p sub r. Those little p's are all going to be the same exact set there. So anyway, but again, if that prime factor was not supposed to be part of it, we'll just take it to the 0th power. Now let's use this this theorem here. And first of all, let's see if we can find the GCD of these two numbers. So here, looking under GCD, it says take the minimum of all of those exponents. So for the 2, we'll have a 3 and a 1, so the minimum would be a 1. For the 3's, we have a 3 to the 1, 3 to the 0. The minimum is 0. And 5, the minimum of 0 and 2 is 0. So you end up over here on the right, 2 to the 1 times 3 to the 0 times 5 to the 0. That ends up with giving us just a 2. So we could say that the GCD of 24 and 50 is a 2. Now you might be saying, well, I could have come up with that a different way, an easier way. And that's true, except that when there's larger numbers, sometimes this way is by far the easiest way. Okay, so the GCD is where we've got those prime factors taken to the minimum of the exponents that showed up. The LCM is the same, but we're taking the maximum of those exponents. So we would have 2 to the 3rd, 3 to the 1, 5 to the 2nd. Have to multiply those all out. That would give us the least common multiple. And this also states that first little note there was that x divides y if and only if the alphas are less than or equal to the betas. So let's look and see, are the alphas, let's say that the alphas are the exponents for the 24 and the betas are exponents for the 50. Are the alphas always smaller than the betas? No. In some cases they're bigger, in some cases it's smaller. So we would not be able to say that the 24 divides 50. That's that other point there, that besides finding the GCD and the LCM here, we can also tell if one number divides the other. And in this case here, we have to say no. In neither case, since sometimes the exponents are larger than in the other number and sometimes they're smaller, neither one divides the second. But if I had this, 18, which I could write as 2 to the 1 times 3 squared, and 360 I could write as 2 to the 3rd, 3 squared. In that case, the 360 has, the alphas, if the alphas are in the 18 for the 18s, for 18 exponents, and the betas are the exponents for 360, yes, the alphas are less than or equal to the betas in all cases, so we could say that 18 divides 360. That's all we have for this lesson. I will see you for the next lesson where we will continue talking about integer properties.